Hello, everyone. Thank you for coming to my talk today. First, I would like to apologize for you for not being able to attend in person. As you know, there are many uncertainties in the world. I hope that we are able to meet in person with no hesitation in the near future. So my name is Tomonari Furukawa, and I am a professor and Zen faculty fellow at the Department of Mechanical and Aerospace Engineering at University of Virginia. So my talk is entitled uh, Autonomous Driving Using Road Surface Measurement. Um, I have noticed that there is no keynote presentation associated with the autonomous driving, which is a booming and important topic for this particular 2022. In order that the discussion and the conference becomes more active, I decided to just touch the uh, basis of autonomous driving. This is a little, about my research, but I hope that you'll enjoy my talk. So I always like to collaborate with people, and the um, in order for the future collaboration, I would like to just briefly discuss about where I am working at. So as I mentioned that I am working at University of Virginia. It is, particularly in the United States, a very famous university in a sense that it was founded by Thomas Jefferson, the third president of the United States. It is also one of the oldest universities in the States. And because of his construction and design, it is uh, uh, the UNESCO World Heritage. The It is in fact the only campus specified as the World Heritage in the United States. So the campus is very, very beautiful and known to be one of the most beautiful campuses in the United States. So if you have a chance to come to Charlottesville or Washington, D.C., it's only 1.5 hours drive from Washington, D.C. So please do let me know. I'm more than happy to invite you to the university. And there I am the director of the Victor Lab. It is not only the autonomous vehicles, but also focused on the autonomous robots. Currently, the lab is inside this whole building, and which has also the very large the indoor facilities doing various tasks. And for the purpose, I have a wide range of robotic vehicles. When doing the outdoor testing, and university also have a very large land, and this is where I do various outdoor tests. Today's talk, I will start with the introducing the history and the state of the art of autonomous driving, and finally address the limitations of the current autonomous driving technology. Um, Followingly, I will say why road surface measurement is important for autonomous driving. Structure from motion-based road profiling, road surface measurement technique is what I uh, proposed, developed with my graduate students. And also, I will present the uh, autonomous defect identification techniques, which we developed using the 3D reconstructed images by the preceding technique. Finally, I will present the autonomous driving using road surface measurement. So autonomous driving is booming, but in fact it is not new. 2000, by 2000, the Komatsu has already introduced the autonomous mining truck into the market by having the uh, uh, project in beginning early 1990s. Of course, this is GPS driven. It is not fully autonomous, but the idea existed, and they were also advancement. The, for the cars, the technology have been progressing in the name of ADAS. Lots of technologies, starting from the cruise control, adaptive cruise control, automatic emergency brake system, lane keeping assist system, traffic jam assist system. There are many technologies have been developed and have been implemented. The 2007, the well-known developer urban challenge uh, was held. The Virginia Tech that I was brought in before uh, came to University of Virginia, became third in this challenge. And after this 2007 competition, the General Motors announced that they are selling the cars that require no driver and allows autonomous driving until parking at the destination by 2018. And of course, it didn't happen, but that's how the autonomous driving beam started. And needless to say that Google uh, and also other IT companies started to join this development, and even the government started to support the development. I'm here showing the level of driving automation, and we were really discussing up to level 5. We do not really know where we are this moment because uh, achieving the autonomous driving in the whole scenario is extremely challenging. And there was a exaggerated discussions. Now we started to tone down a little bit. This is also good because uh, we did not know whether we could achieve the autonomous driving that fast. So although that we have not been able to achieve fully autonomous driving at all, there were uh, also the progresses. Um, but if you just observe by dimensions such as what I am showing here I'm introducing the GPS difficulty, environmental complexity, and also the speed. What we have been able to demonstrate so far are relatively easy problems. But on the other hand, the reason why we don't see the autonomous driving is because the car moves all places. So the environment could become very complex, or it could even go into the tunnels where the GPS is not available. And for this reason, we are not still close to achieving autonomous driving. I also am showing here the environmental complexities in the snow, in the rain. The scene that the camera can see becomes completely different, and then we need to have a more sophisticated techniques to be able to perceive the environment. Industry is taking an approach conservatively solving one after another the problem. As an academic faculty, what I we are trying to do really is to see what technology is going to be needed in the future. So today I'm talking about this road surface measurement. That is also one of the things that we need to see uh, when the technology advances. So the clear difference between what the industry doing and what I have been doing is that the industry just try to see front the long range, and on the other hand, what I'm trying to see is the road surface. Seeing the road surfaces was quite important because the cars are in contact with the road, and the performance of the vehicle, safety of the vehicle is heavily dependent on the road surface. So I'm here showing the vehicle safety versus road condition. The conditions, of course, changes with respect to time, and lastly, that the ill conditions could cause traffic accident, risking the life of humans. So obviously that we have to be able to detect so that we can repair the road, and at the same time that we have to be able to avoid such dangerous conditions. It is not only the road conditions, but also the road type and environmental conditions affect the vehicle safety. So here on the left-hand side, we see gravel road, cobblestone, asphalt, concrete. So each one of them has different friction coefficient, and therefore the vehicle performance changes. And if you also see the rain, snow, or ice, the it is not only the dynamic friction coefficient, but many uh, parameters changes. For example, in here, the friction coefficient is less than 10% of the normal time when we see ice or snow on the road. So therefore, identifying the road condition, road types, also is quite important. Although that the current autonomous driving is not focusing on it. Humans identify road conditions by using some index that have been developed. So, and based on this, we repair the road or we even judge the safety. When we try to also do the autonomous driving, the robotic vehicle must be able to also identify what the human is able to do. So we are using what has been developed to improve our autonomous detection systems. Here, the work that I started at Virginia Tech, that was before I came to UVA. Here we have the two cameras attached at the rear side of the vehicle because we are trying to do the 3D reconstruction of the road offline. In the case of the highway, where we drive the vehicle at the speed of 65 miles per hour, what we see mostly on such a road are the potholes. It is because there are many trucks, heavy vehicles, which heavily use the vehicles, the roads. For this reason, the mechanical pressure creates a lot of potholes. When it comes to the local road, you see cracks much more often than potholes. It is because the roads are used by low-speed vehicles. We do not have to repair frequently and let the cracks uh, exist in there. But of course, the cracks create ultimately the potholes, and therefore identifying the cracks for local roads also becomes quite important. The um, in order for us to identify the potholes and the cracks, what we first look at is the width of the roads to monitor. When we are driving at the 65 miles per hour, the lane widths go up to 3.7 meters. Field, what we find necessary are the two cameras attached close to the both sides of the vehicles. And we also needed to identify the frame rate so that multiple images can cover any point on the surface. Here I'm showing that 4 images are covering a specific point on the road. If we have more than 2 images, essentially we can stereoscopically reconstruct the 3 images. And since we have more images, we are able to make the road surface more accurate. But we are also controlling and determining the frame rate, making sure that we are able to cover a point on the road by multiple images. The car speed also, having said this, keeps changing. So we would not like to just keep the frame rate consistent, because when the car is, for example, stopping at traffic light, we would not like to keep taking images which are identical images. So we control the frame rate dynamically by FPGA. And further, when you're taking images, sometimes there are trees, buildings which create the shade, which makes the image dark. So, and very difficult to also get the clear images. So we are also using the strobe to provide additional light, and at the same time making the image finer, since the images will be primarily created when the strobe is on. And finally, we did the high-speed experiment on the freeway, and were able to, as you can see here, create an image with a motion blur. So this hardware development was the first important progress for us, and then we are able to start moving on to the next, which is the high precision 3D reconstruction. So the diagram here shows the overall approach proposed by our team. So we are on the left-hand side 3D reconstructing from the 2D images. So it is converting into the point clouds and filling the plane and introducing the dimensionality, connecting onto the 2D planes, and then this way that we are able to develop the 3D road surface. And after developing the 3D images, then we are identifying the defects by developing automatic detector for potholes and cracks. So let's start with the potholes. So pothole, as you can see, is geometrically seen. One image is in here, and second image is in here. What we do first of all is to automatically identify the features corresponding to each other, and the correspondences are described here by yellow lines. And then using the correspondences, we 3D reconstruct. 3D constructed in here, and you can clearly see here that the potholes are at a different level. So by observing the 3D configurations, we are able to automatically identify the potholes. We are able to do the test consecutively on the road. So this is a reconstructed the images, combining 900 images. And if you just take a shorter 128 road, and you can, if you just zoom it, and then you can see just right here that the potholes can be detected uh, by our technique. And there, the automatic pothole detection is based on the histograms and many others inside there. And lastly, that it is able to identify the potholes. We also did a test on the various rows, and ultimately we were successful in positive, positive, negative, negative detections very reliably, and concluded that the 95% positive uh, results could be achieved. In addition to the potholes, we are very interested in cracks, but we have to take a completely different approach for cracks, because cracks are very steeply uh, characterized. So it is very difficult to three-dimensionally identify. But on the other hand, because the water comes in and make the steep discontinuity very dark, we can easily identify from the 2D images. So we are detecting the cracks from 2D images. I am not describing details in here, but we have a Bayesian classifier which even identify the types of the cracks and reliably identify the existing cracks on the roads. So the video here is showing 1, 2, 3, 4, 5 different types of cracks. Depending on where the classifier data is located, we are able to identify what kind of cracks we see in on the road. And similar to the potholes, needless to say that the cracks are more difficult to identify, but we are able to identify the cracks very also reliably. So far what I have presented are all offline, and next we need to think how we can apply this to autonomous driving. As I mentioned, the current autonomous driving is not looking at the road profile. Instead, they are looking and perceiving the traffic signs and marks, traffic infrastructure excluding roads, and also the obstacles including cars and pedestrians. As I mentioned that we cannot exclude the roads since the vehicles are in contact with roads. What we are doing, therefore, is to introduce a capability of perceiving the road profile and conditions. And based on this, we want to change the autonomous strategy, trajectory planning, and also the low-level controls. So to leverage the technologies that we have developed, what we did for the hardware settings is to locate the two cameras front and looking down. And similar to what we did for the offline cases, we introduced the same hardware settings and drove the vehicle. When we drive the vehicle on the roads, what we also recognize is that when the bumps exist, we slow down. We see potholes and we take different reactions. Generally speaking, from the naturalistic driving, what we have found is that any defects or artifact which is less than 2 to 3 centimeters, we tends to ignore and bounce. If it is more critical, and then we try to slow down. And if it is very critical, we try to steer and avoid. So you can see that the our autonomous driving technique also changes, and the road providing that for this reason is necessary. Indeed, when we at the end here see the pedestrians, and in such case we stop the vehicle. So lastly, that we were interested in finding out how much we are able to uh, identify the road condition in real time, and here the two images are what we see from the camera. Since it is looking down, first what we need to do is we need to do the transformation and see the images as if that we are seeing vertically from the top. Once we are able to do it, what we need to do is to apply the techniques that we developed for pothole and the crack measurements. Of course, when you try to see far ahead, the 3D uh, reconstruction accuracy significantly drops. So it is not effective. But at the same time, what we found is that we are able to detect the pothole uh, uh, enough so that we are able to avoid in some cases. And one last video that I am showing here is an example. Uh, it is autonomous emergency stop into curve. There are many cases where the driver would not be able to continue their driving. In such cases, the automated vehicles would like to find a roadside which is safe to have the vehicle stopped. In such cases, it is an emergency brake, the hard brake, and the road condition also becomes quite important. The technology that we have developed obviously is useful in such scenarios, and we try to incorporate the technologies that we developed into autonomous driving. I hope that you enjoyed my talk today, and hope to continue the discussions. If you're interested in uh, any of the discussions that I introduced today, please do not hesitate to contact me. And lastly, I would like to acknowledge my wonderful the young generation team members, including postdoc graduate students and undergraduate students. Thank you very much for your attention. And unfortunately, I will not be able to take uh, any questions, but please feel free to send an email to me. My email address is my first name, Tomonari, at Virginia, full spelling, .edu. Thank you very much.